Another simple system where we can experiment and try out the general framework that we had developed is a harmonic oscillator, a single one-dimensional harmonic oscillator. You all know from quantum mechanics the energy spectrum of a harmonic oscillator. This is the harmonic oscillator potential, and you have energy levels that are equally spaced, and the energy of the pth level is given by p plus 1/2 h bar omega. So down here you have the ground state, E0. The energy of the ground state is simply 1/2 h bar omega, where omega is the frequency that characterizes your harmonic oscillator. Let's suppose that for this harmonic oscillator we are given the expectation value of energy. So we are given the expectation value of the Hamiltonian. This is our macroscopic data. Then we construct the macro state of the harmonic oscillator by, as usual, by maximizing the entropy under the given constraint in the form of the expectation value of the Hamiltonian. And this gives us the Boltzmann-Gibbs state, or also called the canonical state, of the form 1 over partition function e to the minus beta Hamiltonian, where, as we have found out by now, beta is the inverse temperature and the z is the partition function. As for the partition function depends on the Lagrange parameter, which in this case is only beta, and it's defined as the trace of e to the minus beta Hamiltonian. The trace is the sum of the trace of an operator is the sum of its eigenvalues. So all you need here is the eigenvalues of the Hamiltonian, or in other words, the spectrum of the Hamiltonian. But we know that for a harmonic oscillator. It's the sum over all p going from 0 to infinity. And then we have the e to the minus beta, and then the eigenvalue EP of the Hamiltonian. For the pth energy level, for the EP, we can insert the formula in blue. We can factor out the 1/2 h bar omega. So we can say, we can factor out an exponential e to the minus 1/2 beta h bar omega. And we are left with the sum over p from 0 to infinity. And then we have e to the minus beta h bar omega times p. So this is the formula, the blue formula for the pth energy eigenvalue inserted into this formula for the partition function, and then we obtain this form. This exponential in the sum we can also write in the following form. It's e to the minus beta h bar omega times p. We can insert here a bracket, and so we can say this is e to the minus beta h bar omega in brackets to the power p. And then you recognize this is nothing but a geometric series here. This is a geometric series. It's a sum, p going from 0 to infinity, and then some term to the power p. And we know the formula for the geometric series. This is, well, we still have this prefactor e to the minus 1/2 beta h bar omega, and then the formula for the geometric series, that's 1 over 1 minus e to the minus beta h bar omega. And then we can take the prefactor back into the formula and can also write that as 1 over e to the 1/2 beta h bar omega minus e to the minus 1/2 beta h bar omega. And this finally you can also write as 1 over 2 times the hyperbolic sine of 1/2 beta h bar omega. So this is the partition function of a single harmonic oscillator. Did you understand this derivation? It's always the same pattern. You are given a quantum mechanical system with a certain Hamiltonian. Now, very often you work with a canonical state. So you have a partition function of the form trace e to the minus beta h. Now, in order to calculate the trace, you need the spectrum of the Hamiltonian. And if the system is simple enough, then there's a simple formula for the spectrum. You insert that formula into the formula for the trace. And in many cases, in simple cases, you have an infinite series for which you have a formula, and you can calculate the partition function. And in this case, it gives this formula 1 over 2 times this hyperbolic sine. Now, as I told you, once you have the partition function, then basically the formula for the partition function already contains all the thermodynamic properties. So from there you can develop and derive all the interesting thermodynamic relations. So let's do that in this example of the harmonic oscillator, and let's derive from this partition function a few interesting thermodynamic properties. One interesting thermodynamic quantity variable is the internal energy. How do we derive the internal energy from the partition function? We take minus the partial derivative with respect to beta. Now, this is something that you can see from the Guggenheim square that we discussed last time. And given that beta and u appear so often, you can also memorize this particular formula. This will be used over and over again. The internal energy is minus partial with respect to beta of the log of the partition function. Now this is minus 1 over partition function dz over d beta. The partition function was 1 over the 2 times the hyperbolic sine. We can factor out the 1/2, and we have 1 over the hyperbolic sine. The derivative of that is minus 1 over the hyperbolic sine squared times the inner derivative of the hyperbolic sine, that's the hyperbolic cosine, and then we have the inner derivative of the argument of the hyperbolic sine. And remember the argument that was 1/2 h bar omega times beta, derive that with respect to beta, gives you 1/2 h bar omega. Now there are a few cancellations. First of all, the minus sign cancels out. Then you have one of the, over the partition function. The partition function is 1/2 times the hyperbolic sine. So 1 over the partition function is 2 times the hyperbolic sine. So there's a 2 in there that cancels with the 2 here. And then there's a hyperbolic sine which cancels with one of the hyperbolic sines here in the denominator. So this 1 over partition function cancels out, and what's left in this calculation is, let me take this in front, the 1/2 h bar omega, and then we have the hyperbolic cosine over the hyperbolic sine. And when we can factor out once again an exponential e to the 1/2 h bar omega times beta, and what remains is an e to the beta h bar omega plus 1 over e to the beta h bar omega minus 1. This is the formula for the energy, the expectation value of energy of a single harmonic oscillator at temperature T or inverse temperature beta. So we have energy as a function of temperature. It's interesting to look at two opposite limits, either very low temperature or very high temperature. Let's start with the low temperature limit. T goes to 0. This implies that the inverse temperature beta goes to infinity. Now this implies that in this ratio the exponential dominates. It's much larger than 1. So numerator and denominator both become very large. The plus or minus 1 becomes negligible. So this ratio approaches 1, and this means that the internal energy approaches 1/2 h bar omega, which is the ground state energy, which is exactly what you would expect, that as the temperature goes to 0, the system settles in the ground state. We can look at the opposite limit, where T becomes very large, and in particular much larger than the typical energy scale of the harmonic oscillator, much larger than h bar omega. Sorry, I should say not T is much larger than h bar omega, but KT. KT is much larger than h bar omega. This implies that beta h bar omega, so the exponent in this exponential, becomes very small. It becomes much smaller than 1. This implies that the exponential can be approximated to lowest order by first order Taylor expansion. So you can approximate that by 1 plus beta h bar omega. And this implies that in the numerator you have approximately 2 plus beta h bar omega. And in the denominator, the 1 cancels out. In the denominator, you have approximately beta h bar omega. So you have, let me write this down, plus 1 divided by minus 1. This is approximately 2 plus beta h bar omega divided by beta h bar omega. Now in the numerator, the beta h bar omega, we said this is much smaller than 1, so this is negligible compared to the 2. So we have 2 over beta h bar omega. When you finally multiply that with the 1/2 h bar omega in the formula for the internal energy, then the h bar omega cancels out. The 1/2 cancels against the 2. And all that is left is U is approximately 1 over beta, which is kT. So for large temperatures, temperatures that are large compared to the, or where kT is large, very large compared to the typical energy scale of the harmonic oscillator, h bar omega, it holds that the internal energy is approximately given by kT. Next, let us turn to the entropy. Remember that the entropy is related to the log of the partition function, again via the Guggenheim square, which in the case of a canonical state is the relation log of the partition function plus beta times U, beta times internal energy. Let's use the formulas that we found on the 2 previous pages. We have the partition function as a function of temperature, and we have the internal energy as a function of temperature. So this gives us the entropy. When we insert these 2 results, this will give us the entropy as a function of temperature. The partition function was 1 over 2 times the hyperbolic sine, so we take the log of that, and we obtain then minus the log of 2 times the hyperbolic sine of 1/2 beta h bar omega. And then for the internal energy, we had 1/2 h bar omega, and now this is multiplied with a beta, so we have beta h bar omega, and then we have this ratio e to the beta h bar omega plus 1 and e to the beta h bar omega minus 1. So this is the entropy as a function of temperature. Now, you must be careful that temperature or inverse temperature is not, we learned this is not the natural variable of the entropy. The natural variable of entropy is the energy, not the temperature. So when you want to check thermodynamic relations starting from the entropy rather than the log of the partition function, you will have to find entropy as a function of energy. That's something that we will do in the next step. But here, at this point, we still have entropy as a function of a non-natural variable for the entropy, namely the temperature. This is a rather complicated expression, but again, we can look at limits. First of all, the limit T going to 0, low temperatures. In that case, remember the partition function. There was this geometric series. If the temperature is low, then beta h bar omega is large. So e to the minus beta h bar omega, that's the expression that occurs in the way you have the geometric series. This e to the minus beta h bar omega becomes very small. So only the first term in the geometric series contributes, where you take the 0th power of that, because this gives 1. And all the higher terms in the geometric series become very small. So you can stick with the first term in the geometric series, which is e to the minus beta h bar omega to the power 0, and this gives 1. And then you had the prefactor before that, e to the minus 1/2 beta h bar omega in front of the sum, and the sum simply gives you 1. So this is the partition function for low temperatures. And then, of course, it's easy to take the logarithm. This simply gives you minus 1/2 beta h bar omega. Now, in this limit, it's easy to write down the entropy, because for log z, we say this is minus 1/2 beta h bar omega. And for beta times u, we said on the previous page, as the temperature goes to 0, the internal energy goes to its ground state, to the ground state energy, which is 1/2 h bar omega. So beta times u goes to 1/2 beta h bar omega. And you see that these two terms exactly cancel. So the entropy goes to 0. So we find for the harmonic oscillator, as the temperature goes to 0, the entropy goes to 0. And this is perfectly plausible, because it means that the system settles in the ground state. The ground state is a pure state, and a pure state has entropy 0. Finally, without going into details, maybe this will become an exercise on the next problem set. As the temperature becomes very large, the temperature goes to infinity, so we look at the asymptotic behavior for very large temperatures. You can convince yourself that asymptotically the entropy grows as the log of temperature. So that's different from the asymptotic behavior of the energy. We saw on the previous page the internal energy goes as like the temperature, it goes like kT. It's linear in T for large temperatures. In contrast, the entropy grows logarithmically with the temperature. Now, as I said, beta is not the natural variable of energy, of entropy. So if you want to work with the entropy function and derive from that other thermodynamic quantities, you should have entropy as a function of its natural variable, which is the internal energy. So somehow you must make the transition from S as a function of beta to S as a function of U. How do you do that? The basic idea is the following. You have, if you want S as a function of U, always modulo the Boltzmann constant, you know this is a log of the partition function plus beta times U. Now this holds generally, regardless of which you take as the independent variable here. So this relationship between entropy and the partition function, log of the partition function, holds generally. What we have so far is, on the right-hand side, we have the log of the partition function as a function of beta, we have the internal energy as a function of beta, and of course the combination then gives us the entropy as a function of beta. But we want the entropy as a function of U. The way we can achieve that, if we can, we have the internal energy as a function of beta. If we can invert this equation and solve for beta as a function of U, then we can express on the right-hand side, we can express all the betas that appear as functions of U. And if we succeed in doing that, then on the right-hand side, we have the log of the partition function as a function of U, plus beta as a function of U times U. So on the right-hand side, we have a function of U, and this is then the entropy as a function of U. This is the basic idea. So we should start with the energy as a function of beta. This was this function here that we found 2 pages earlier. Energy as a function of beta. We can invert this equation and solve for beta. This gives us beta as a function of U. And I hope you trust me, but you should verify for yourselves that this is 2 over h bar omega, the inverse hyperbolic tangent of h bar omega over 2 times u. So this is the first step, that we invert and we solve for beta as a function of u, and this gives this formula here. We could now use this formula. So we have the partition function as a function of beta. Then we could use this formula here, beta as a function of u, insert it into the formula for the partition function, and then obtain the partition function as a function of u. This is straightforward, but perhaps a bit messy, because you have to work with these hyperbolic functions and their inverses. There's, in this case, a little trick that allows you to arrive at the result a bit more quickly. And this is the following observation. Remember that the internal energy could also be written as 1/2 h bar omega, and then the ratio of the hyperbolic cosine over the hyperbolic sine. The hyperbolic cosine, in turn, can always be written as 1 plus hyperbolic sine squared of the argument over the hyperbolic sine. But now remember that 1 over 2 times the hyperbolic sine, that was the partition function. So in fact, in this expression, we can replace 1 over 2 times the hyperbolic sine by the partition function. And then we still have the square root, 1 plus, and then we have the hyperbolic sine squared. But again, we know the partition function is 1 over 2 times the hyperbolic sine. So the hyperbolic sine is 1 over 2 times the partition function. And the square of that is 1 over 4 times partition function squared. And then we can take the partition function that's now in front of the square root, we can take that under the square root, and we can write that as h bar omega square root of partition function squared plus 1/4. And this you can solve for the partition function now as a function of u. And this gives the square root of internal energy over h bar omega squared minus 1/4. And now we have all the ingredients that we need. We have beta as a function of u. We have a formula, and this formula we insert up there. And then we have the partition function as a function of u, and that formula we insert here. And in combination, this gives you the entropy as a function of u. I'm not going to do that explicitly, it's just inserting these two expressions up there in the general formula. It's nothing new, really. And then you have what you want. Quite generally, what we have just done, going from our starting point was the partition function of the log of the partition function as a function of beta. That was the first thing that we had calculated. And now, via these intermediate steps, we have obtained the entropy as a function of u. So in our Guggenheim square, what we have done effectively is we have gone from the log of the partition function to the entropy. The log of the partition function was a function of its natural variable beta, and the entropy is now a function of its natural variable u. And this transition from log z as a function of its natural variable beta to the entropy as a function of its natural variable u, this amounts mathematically to a Legendre transformation. And here on this page, together with the previous pages, you have seen how you do that in practice. Yeah? So you use the general formula, that's the first line on this page, that relates the entropy to the log of the partition function, plus beta times u. But initially you have the problem that you get then s as a function of the wrong variable. In order to get s as a function of its natural variable u, you still have to do this inversion. You have to express beta as a function of u up until you get s as a function of its correct natural variable. And that's an example of the Legendre transform. So to conclude the discussion of the harmonic oscillator, let us check one of the thermodynamic relations. Now that we have the entropy as a function of its natural variable u, we can verify that the partial derivative of entropy with respect to its natural variable u indeed gives the conjugate of u, namely beta. In order to do the calculation, we will need, amongst others, the partial derivative of the log of the partition function now as a function of u with respect to u. Now this is 1 over partition function, partial of z with respect to u. Remember the formula for the partition function as a function of u, that was this square root of u over h bar omega squared minus 1/4. The derivative of a square root is 1 over 2 times the square root. And then we need the inner derivative of the expression under the square root. That was u over h bar omega squared. The derivative of that is 2 times u over h bar omega, and finally the derivative of that with respect to u is 1 over h bar omega. The 2 cancels out, and we are left with 1 over h bar omega squared. Then we have a 1 over partition function squared, and we have u itself. So this is the partial of the log of z with respect to u. Another derivative that we will need is the partial derivative with respect to u of beta regarded as a function of u. Now beta in turn, that was 2 over h bar omega times this inverse hyperbolic tangents. The prefactor remains 2 over h bar omega. The derivative of this inverse hyperbolic tangents is 1 over 1 minus, and then the argument of this hyperbolic function squared, that was h bar omega over 2 times u squared. And then the inner derivative of the argument, this is first of all the prefactor h bar omega over 2, and then we have the derivative of 1 over u, this is minus 1 over u squared. And when we simplify this a little bit, you see there are again some cancellations. These 2 factors cancel, and we are left with minus, and then we can factor out h bar omega squared, and we have a 1 over u over h bar omega squared. So I take in the 1 over u squared minus 1/4. But this expression here, you recognize, this is what we found. The denominator is the partition function as a function of u squared. And now we can use these intermediate results and try to calculate the partial with respect to u of the entropy. The entropy is a log of the partition function plus beta u. So first we have the partial of the log of the partition function. That's the result that we had on the first line. This is 1 over h bar omega squared 1 over z squared times u. And then we have the partial derivative of beta u with respect to u. Product rule, this first of all gives us the partial of beta with respect to u, which is the result of our second line. So this is minus 1 over h bar omega squared times 1 over partition function squared times u. And then we have beta times the partial derivative of u with respect to u, but this is 1. Yeah? And here you see that the first 2 terms exactly cancel, and what remains is beta, and this is exactly what we expected from our general considerations. So you can do a lot of gymnastics here in these specific examples and verify and practice that the general thermodynamic relations all come out very nicely.